Alright, so in this lesson we're going to start looking at the intensity of sound. And the way we define intensity of sound is the amount of power passing through a surface divided by the area of that surface. So the assumption we make is that sound is emitted uniformly in all directions. That if you have a speaker, the sound is going to be emitted in all directions away from that speaker. And so if we look at kind of a source of sound, generally the direction that sound is going to travel is kind of in a sphere outward from it. And so the area of a surface is going to be related to how far you are away from that source of sound. So the intensity, we've defined it as power divided by area. And so intensity is equal to power divided by the area of the sphere you're sitting at, where r is the distance away from the source of sound you are. So P divided by 4 pi r squared. So what you really get is an intensity in watts per meter squared when you work this out. So in the picture above, two observers of fireworks display. When the sound reaches observer 2 at a distance of 640 meters, it has an intensity of 0.1 watts per meter squared. What is the sound intensity at the location of observer 1 at a distance of 160 meters? So if intensity is equal to power over 4 pi r squared, we know the power, the amount of energy emitted by the source doesn't change. So if we rewrite this, we could say power is equal to intensity times 4 pi r squared. We know power 1, power 2 are equal to one another. Same source of sound. So I1 4 pi r1 squared equals I2 4 pi r2 squared. And the only difference, 4 pi's cancel, and so we get I1 r1 squared, I2 r2 squared. And so we can solve that for I1. And when we do our calculation, we get 1.6 watts per meter squared. So that means that the sound intensity at observer 1, who is about 500 meters closer, a quarter the distance, is 16 times bigger. So, which makes sense if we think about it. If distance squared, increasing distance squared decreases your sound, decreasing that distance squared should have the same effect on your sound. Now the weird thing about intensities is that humans are actually able to hear sounds with a wide range of intensities. What's called the threshold of hearing is 1 times 10 to the negative 12 watts per meter squared, a very, very soft sound. You can imagine this like a mosquito buzzing by your ear, that type of sound. However, sounds that we can hear up to 1 watt per meter, so something that is, well, 10 to the 12th times bigger in terms of intensity, that's where you actually start to cause hearing damage when you get long-term exposure to those types of sounds. 10 to the 12th is like 1 trillion times bigger. And then it's actually when you get to 10 watts per meter where the sound actually becomes painfully loud, where it'll be physically uncomfortable for you to be around that sound. The cool thing about sound is that you don't hear intensity on a linear scale. 0.5 watts per meter is not half as loud as 1 watt per meter. And part of the reason for that is that this intensity level or the scale is so large, or this range of values is so large, that it'd be very difficult for you to distinguish between two very soft sounds if you also had to be able to hear very loud sounds without breaking your eardrum, right? So what I would usually say as a good example is it's very important for your body to be able to distinguish between two soft sounds playing or at the same time, but not very important for you to distinguish between a loud sound and a very soft sound. If you go back and think about our ancestry, maybe tens of thousands of years ago, being able to hear one predator creep through the bush versus two predators creep through the bush might be a useful piece of information. The do I stand here and fight, or do I try to get out of this situation? Well, whether or not there's one lion there or two lions there maybe makes a difference in what decision you pick. Now, kind of in a related example, if that lion is charging at you roaring and there's another one creeping through the bush, the fact that there's a second lion creeping through the bush is probably not all that important in terms of a piece of information. Probably you hearing that one is more important to get away from it. Or if there's an elephant charging at you and a lion sitting in the bush waiting for you, you probably want to run away. The fact that there's one lion or two lions there doesn't really matter if there's an elephant charging at you. So your body actually hears sound on what's called a logarithmic scale based upon powers of 10. Your body can distinguish between very, very soft sounds, but if you get to a loud sound and a very soft sound, it's the same as a loud sound. So using a logarithmic scale to describe intensity level is actually more convenient. And we use a logarithmic scale, it's called decibels, to describe how loud a sound really is. And so the calculation of a decibel is we take 10 decibels and multiply by the logarithm of the intensity of sound divided by the threshold of hearing, which is 1 times 10 to the negative 12th. So basically we're comparing how loud is this sound compared to the softest sound that humans could possibly hear, and then divide it by, or take the logarithm of that ratio and multiply it by 10. What this means is the threshold of hearing is a decibel level of 0. Something like leaves blowing around should be about 10 decibels. You could whisper at about 20 decibels. Normal conversation, 65. If you're sitting inside your car, about 80. And it's really when you start to get to live rock concert where you get to 120 decibels. Sometimes I'd throw jet engine. If you're standing next to a jet engine, it's usually about 150 decibels. These would be sound intensities that are going to start to cause damage if you are experiencing them long term. So let's do a quick calculation and say audio system 1 produces an intensity level of 90 decibels and audio system 2 produces an intensity level of 93 decibels. And we want to determine the ratio between the intensity of sound 2 and sound 1. Doesn't look like it's very different. 90 to 93, that's a change of 3. That's not that big of a deal. But let's see if we can find the actual ratios of intensity. And the thing to remember is this is actually a logarithmic scale. It's not a linear scale. So if we go to calculate out what the intensity looks like, we divide decibels by 10, get rid of logarithm by doing 10 to the power of both sides, and so the intensity of sound is really 1 times 10 to the negative 12th times 10 to the decibels over 10 power. And so if we take and divide that out, some things to point out as the initial intensity of sound divides out. We can combine powers of 10. The way to do that is if you have something with an exponent divided by something with an exponent, that's the same thing as subtracting those exponents. And so we can now actually calculate that out, that the difference in intensity is 10 to the 9.3 minus 9.0 power, or 10 to the 0.3 power, or 2. The intensity level of a 93 decibel sound versus a 90 decibel sound, the intensity of that 93 decibel sound is twice as big as that 90 decibel sound. One thing to point out is if you go 90 to 100, the intensity actually is 10 times as big. Every 10 you go up, you get 10 times as big. Now I might ask, how common is a logarithmic scale in science? And I'm going to say it's relatively common. It shows up in other areas as well. If you look at something like earthquake intensity, that's really a logarithmic scale. What's called the Fujita scale to measure tornado intensity is a logarithmic scale. The Saffir-Simpson scale, which measures hurricane or cyclone intensity, is a logarithmic scale. For those of you who are in chemistry or interested in chemistry, pH is a logarithmic scale. So logarithmic scales show up in lots of different places in science, so it's sometimes important to know how to deal with logarithms. So that's a quick overview of intensity of sound in this unit of decibels. It is kind of a strange unit, but remember that it's a logarithm. It's not a linear thing. So the difference between 90 and 93 is not a small difference. It's double in terms of intensity.